Okay, I'm glad to have this occasion to tell to the audience a little bit about chemistry. And let me start with my talk, which has as title Steps Towards Life and Thought, but of course it's very short, so the title is much too broad, but I would like to show that it has something to do with chemistry. In order to do that, we have to start very early, which means we will start with the origin of the universe. The Big Bang. After the Big Bang, the universe was very hot. There was no chemistry, it was only physics. That's the age of physics. Then atoms formed, molecules formed, and this was the age of chemistry. Molecules in our universe became more and more complicated, more complex, they became bigger, they began to associate, and a new property appeared, which has to do with what is the matter of this talk. Life on Earth started around here. That's the age of biology. But evolution continued and a new feature appeared, which was thinking. That is represented here by this statue here, the thinker of Auguste Rodin. And this is Steps Towards Life and Thought, and we sit here. Of course, evolution of the universe will not stop at this stage. It will continue, and there will be new properties appearing. Now, this evolution towards complex matter leads to the fact that in our universe, the bricks of visible matter in our universe are those contained in the periodic table, which was initially proposed by Dmitry Mendeleev in 1869. This table tells us what are the bricks of visible matter in our universe. That means all objects, all entities, part of visible matter will be built up with these bricks, these elements, and this is the playground of chemistry. Chemists use these bricks and build complex entities, molecules, materials, and then try to give them also to look for properties, to understand how to do it, and to find interesting new properties. Now, molecular chemistry started initially by building molecules from atoms. And milestones there can be seen as in 1828, in the laboratory of Friedrich Wöhler in Germany, urea could be made from another chemical. And 150 years later, this very complex molecule, vitamin B12, was made in the laboratory of two professors, one at Harvard, Woodward, and the other one at ETH in Zurich, Albert Eschenmoser. Of course, as you can see, molecular chemistry has made a lot of progress in this time, since it was possible to go from making urea in the laboratory to making this vitamin B12. It's a very big molecule which is present also in our body. And these were the combined efforts of many co-workers in the group of Robert Burns Woodward and of Albert Eschenmoser. But molecular chemistry did not stop at this stage. It continued and became more and more rich in new reactions, new molecules were made, new materials were made, and so on. So it is very active science and continues. However, we have to ask a question. The question is, what happens when molecules get together? For instance, here I show a cancer cell and two killer cells. The killer cells must find the cancer cell and destroy it. How do the killer cells know that the other one is a cancer cell? There must be something telling them that the partner, the other one, is a cancer cell. Similarly, the HIV virus, these blue dots here, can infect a white blood cell when it goes into contact with it. How does the virus do this? How is it possible for the virus to know that it has reached the goal? So something must happen between the killer cells and the cancer cell, between the HIV virus and the white blood cell. And this is a process where molecules touch each other and they associate. This is a chemistry which is beyond the molecule, a chemistry which is between the molecules. Molecular chemistry is the chemistry of the molecules themselves. Supramolecular chemistry is the chemistry of assemblies of molecules, of what molecules do when they get together, when they touch each other. And this supramolecular chemistry and the interactions are at the basis of the recognition between a killer cell and a cancer cell of a virus and its goal, its target. So it's a chemistry of molecular assemblies, of populations of molecules, and it depends on the interactions between these molecules. The three main features are that molecules can recognize one another. So the killer cells can recognize cancer cells through contact of the molecules which are present in their membranes. And of course, reactivity and transport of molecules through membranes are also other features of supramolecular chemistry. But the most important basic one is molecular recognition. How do molecules recognize one another? In order to illustrate that, but the best is to use as a model the storage of information in our genome. You know that living organisms on our planet have a genome which defines what they are. There's genetic information, and this genetic information is written with just 4 chemical letters, which are shown here. These are 4 chemical groups which write the genome of all living organisms of our planet. And of course, 4 letters are enough for defining a living organism on our planet Earth. Now, this is a storage of the information. A given sequence of these chemical letters make the genome the information which will distinguish, for instance, a tomato from an elephant. The reading of this information is on the supramolecular level. The storage is in the molecule. The reading is by contact between these letters of the genetic information. 2 letters can pair up by making 2 binding interactions between them, and 2 other letters, the 2 others, make contact by 3 interactions. And it is this binary system, 2-3, 2-3, 2-3, which is the way in which the molecular information stored in the genome of living organisms can be read out. The 2 of such chains, which are represented on the left, can wrap around each other and form then the very well-known DNA, double helix of DNA. So I insist again, this is molecular storage and supramolecular reading, which means that chemistry is not only a science of the structure and transformation of matter, non-living or living matter, but it is also an information science. Chemistry is also the science of informed matter. And of course, this is amplified, this is at the highest level in what happens in living organisms, the way they store and process information. The storage is on the molecular level. Each molecule has molecular information, and the processing of this information occurs at the supramolecular level between molecules. Now, of course, one is usually interested, especially in a general talk like the present one, and knowing what are the applications. So let me just briefly show you some applications of this supramolecular chemistry. Biologically active substances can be discovered. This is drug discovery, and they depend on molecular information. They depend on molecular recognition, because a drug, a pharmaceutical compound, is a synthetic molecule which is designed for a biological target. We have also made a unit, which you see here, a sort of a red luminescent molecular species, which has been used for developing medical diagnostics apparatus, shown here on the right. Gene transfer can also be operated, which means one can take a gene, a piece of DNA, and introduce it into a cell so that the cell produces a product, a protein, and this is called genetic modifications. And I think we need these modifications. Genetically modified organisms are very important. And finally, I would like to show also some biomaterials which have been made in the field of supramolecular polymers. Supramolecular polymers were developed, started in 1990, and then in 2013, these supramolecular polymers, a new class of polymers, was used to make cardiovascular implants for children. And this was done by a small company in the Netherlands and used for reconstructing the heart of children who had a severe congenital cardiac malformation, and this was done in Moscow. Here is in 2013, 4-year-old Dominika was operated by Professor Leo Bokeria, and many of you must know him, at the Bakulev Scientific Center for Cardiovascular Surgery. So this meant that these supramolecular polymers had been transformed, had been designed into biocompatible polymers to make these cardiovascular implants, which have now been used in many more children than 10, and also heart valves have been made by the same small company. This is a very important application, of course, and for us it was extremely satisfactory to see that the initial concept was transformed into something which was useful for mankind. Now, another property is that these supramolecular type of polymers are also self-healing. Here you see a film which is cut in 2 pieces with scissors. Then you superimpose the 2 ends, you press with your finger in the middle here, and you can stretch because now it has healed. In other words, these type of polymers can form films which then are self-healing, which can repair themselves. Now, the main feature which is of interest, especially in the development on the steps towards living systems and thinking systems in our universe, is that matter is able to self-organize. As an example, I give you here the self-organization of a tobacco mosaic virus. It's a virus, like all viruses, they assemble spontaneously from the bricks which they are made of. This virus, the tobacco mosaic virus, is an assembly of 2,130 protein subunits, which spontaneously get together and form the virus particle. It is a programmed system. There's information for building the virus is contained on the surface of these proteins, on these proteins which form the bricks of the virus, and then spontaneously they assemble and lead to the final particle, which means it's a sort of a programmed chemical system. The system operates by itself spontaneously in a way which is programmed by the interactions which are present and by the supramolecular way in which they then assemble together. Now, in the laboratory, this is an important process to experiment also. And I give you just one type of example, the case where molecules capable of binding metals as connectors were used to generate a variety of complex architectures of different types by designing the correct molecules, which are the bricks, and using the correct connections, which are the metal ions. Let me quickly show you a few. One can make a double helix and a triple helix in the laboratory. These 2 helices, when we made them, they were not known before, and especially they have nothing to do with DNA. It was just a way to show that one can design systems capable of spontaneously leading to a double or a triple helix. Here is a grid-like type of entity. That is a circular architecture, and here is a sort of a cylinder where you see 4 planes which are held together apart by these linear molecules, and they are connected by these 12 metal ions. So in this specific case, 3 linear molecules, 4 flat ones, 12 metal ions spontaneously assemble to generate this nanocylinder. I would like to insist on one thing, which is important perhaps for people who listen to this type, are part of this meeting also. Self-organization of such complex architectures can be of great interest for nanoscience and nanotechnology, because it's a way to generate spontaneously complex architectures. And this is, of course, the ultimate way of fabrication, because it's a spontaneous build-up of a device from its building blocks, thanks to the way the building blocks are designed, so they can spontaneously assemble into the desired functional architecture. Now, this chemistry has developed over the years by designing the objects and so as to produce the ones you want to make. But the next step, just to indicate very briefly, the next step is to make also systems where the system is able to select the bricks it needs to build itself up. And this way, if the system has diversity of bricks and dynamic ways of assembling them, they have also the possibility to adapt when the conditions change. So the step which is now being pursued in this field of research is, on one hand, to go beyond the simple design and to try to build up systems which will operate also a selection, choosing their own bricks so as to generate a final architecture and being able to react to the environment so as to adapt to it. And this area is called adaptive chemistry. So chemistry has started with molecular, being molecular, then it became supramolecular by molecules binding together. Then it became organized, dynamic, adaptive, and of course, these are progressive steps towards more and more complex forms of matter, towards living matter, towards thinking matter, ultimately on our planet at least. So I would like to stress that you may have noticed that the essence of chemistry is not just to discover what already exists, but also to create novel expressions of matter. The book of chemistry has to be written, not only be read. Of course, we have to read the book which has been produced by nature, which already exists, but in fact, the chemists can then write new books. The same way, the score of chemistry has to be composed, not just to be played. So chemistry has creative power to create new objects. And this has very aptly been described by somebody who was not a chemist, but Leonardo da Vinci. He was a great scientist, he was a great engineer, and he was a very, very great artist, as all of you know. He wrote a very interesting sentence, a very powerful sentence, which is written here, where he says, "Where nature finishes to produce its own species." This is all the things, everything which is around us in the natural world. Man begins using natural things, using the bricks of our universe, the periodic table of the elements, in harmony with his very nature. That means in agreement, in harmony with the laws of physics, which control everything that is happening in matter, to create an infinity of species. This is a very strong sentence, especially for a person who is also an artist. To create an infinity of species, meaning to be able to build up all these worlds which do not exist yet in the universe of all possible worlds. So this is not just natural, but it is man-made. Man-made means building all these worlds which await to be created at the hands of the scientists. In the past, the transfer of science and technology and knowledge happened between animal and mankind. In the present, it happens between two people, this transfer of knowledge and of technology. What will happen in the future may be this. I want only to show one thing. I do not say here that we will only shake hands with robots, but I would like to insist on the fact that we will transform ourselves. In fact, we have already transformed ourselves. If you have a cataract operation, you have a new lens in your eye. If you have new teeth, which are implanted, or if you have, for instance, like Dominica, I showed a new piece of material in your heart. This is not natural. We have been modifying ourselves and we will continue to modify ourselves. We will have to accumulate the knowledge which allows us to do that. So I would like for ending to cite the famous sentence of a German mathematician, David Hilbert, when he wrote, "Wir müssen wissen, we must know." And this was already the conviction of a scientist, which is the conviction that we must know. And then science will allow us to know. Wir werden wissen, we will know. This is what drives scientists, what drives research to find new knowledge. So science shapes the future of humanity, and our path will lead us from the quest of knowledge to the control of our destiny. The knowledge we accumulate will allow us now to take our destiny in our own hands to control our destiny. This is why young people especially, but everybody should try to learn some science, know science, because science shapes the future of humanity. Science, basic first, accumulating knowledge and applying it through technology. So all of you, please participate. Thank you very much for your attention.
Мы – транспортно-логистический холдинг «Российские железные дороги». Мы развиваем транспортную инфраструктуру страны, строим новые станции, вокзалы и создаем новые возможности для вашего бизнеса. Лучшие скоростные и высокоскоростные поезда сделают ваше путешествие комфортным и безопасным. Мы – локомотив экономики. Сотни миллионов тонн грузов ежегодно. Развитие науки и социальной сферы – это наш вклад в благосостояние страны и ваша уверенность в завтрашнем дне.
Я новая Hyundai Creta. Hyundai.
Есть история фантастическая. Есть история сказочная. Есть страшная история. А есть история реальная. Юка всегда реальная история и диагностика автомобилей с пробегом. Юка – официальный сервис Hyundai. Смотрите историю и диагностику автомобиля и покупайте его онлайн.